Welcome to Kiko at TechGo, your ultimate destination for discovering innovative research concepts, engaging mini projects, and exciting tech endeavors. In the previous video, I discussed the concept of an electrostatic clutch, covering its definition, the underlying theory of its mechanism, existing research, and the identified issues and gaps along with our proposed solution. Following that, we demonstrated the fabrication process of the suggested electrostatic clutch and conducted its testing. As you may recall, during the initial testing phase, the clutch's holding force was nearly non-existent. Through further literature review, we pinpointed several key factors contributing to this issue: low electric field, conductivity, dielectric constant, and space charge accumulation. Among these, space charge emerged as the primary challenge. In the video, we elaborated on our strategy to address the space charge problem by employing AC voltage instead of DC voltage. Consequently, you witnessed the significant improvement in the clutch's holding force output, demonstrating the effectiveness of our proposed electrostatic clutch design. In today's video, I will be explaining how to determine the holding force of the proposed electrostatic clutch. To analyze the time-dependent behavior of the maximum friction force, we vertically mounted the clutch onto a custom-built pull testing machine and applied voltage using a DC-DC boost converter power supply and an H-bridge circuit. Initially, you can observe that the electrodes are able to move freely, indicating that without the application of voltage, there is no resistance encountered during electrode movement. However, upon applying voltage, you will notice that the electrodes are no longer able to move freely. As the voltage is applied, the force gradually increases until it reaches its maximum, at which point the electrodes begin to slip. Utilizing the output data from the load cell, we measured the maximum holding force, which we recorded as the maximum friction force of the proposed clutch. Furthermore, you can observe that when a known weight is suspended from the clutch while voltage is applied, the clutch effectively holds the weight. However, upon removal of the voltage, the clutch promptly releases the weight. Our subsequent objective was to determine the force versus clutch displacement. To achieve this, we utilized the same experimental setup as employed in finding the maximum holding force, which consists of a custom-made pull tester machine equipped with a load cell. Furthermore, for this experiment, we employed the Tracker software to monitor the clutch displacement and position. Tracker is a freely available video analysis and modeling tool based on the open-source physics Java framework, primarily intended for physics education purposes. Initially, we established the X and Y axes and delineated the path of the movable electrode. Subsequently, we introduced a calibration stick, as demonstrated in the video, to align the recorded video values with real distance measurements. Following this, we proceeded to track the position of the movable electrode. In doing so, we utilize a point mass to track its position as depicted in the video. Subsequently, we recorded the output results from the software and generated a comprehensible graph. In the upcoming video, I will delve into whether the clutch's holding force is sufficient for real-world applications or if further enhancements are necessary. Stay tuned to my channel for more updates. Please subscribe to my channel, Kiko at TechGo, and hit the bell button to receive notifications. Additionally, I would greatly appreciate it if you could like, comment, and share the video. Thank you for your support.